Okay, so we left off talking about shear stresses in beams. We talked about bending stresses, and we then introduced the concept of shear stresses, and we had the equation that the shear stress tau was equal to VQ divided by IB. And we defined all of those terms last time. V was the shear from the shear diagram. Q was the only tricky thing. That was the first area moment. So the integral of y dA, which really amounted to the area above where we're trying to find the shear times the distance from the neutral axis to centroid of that said area. I was, of course, the second area moment, or the area moment of inertia, and B was the width of the beam. The beam had to have parallel sides. So that's our equation. So what I'd like to do is, given a 4x6, which is really 3.5 by 5.5, we'd like to plot shear over the section, assuming that the shear force is 2,000 pounds. So graphically, what I have for the cross section would look something like this. If we were to cut a 4x6 beam in half and look at the end of it, we would have then the center here, which is the neutral axis. And what I'm going to do is I'm just going to hypothetically say, well, let's say that I want to find the shear at that point right there. Okay, so there's some area above that. So let me try and put down my equations here. I think this is, 3.5 there, and then we're going to have, it's half of 5.5, 2 3/4, 2.75, and this will be 2.75. So if I inventory what I have V is 2,000 pounds. I have that the base dimension, that's the same for this thing, 3.5 inches. That's easy. Then we could use that for a rectangular section, base times the height cubed divided by 12, which is 48.5 inches to the fourth. Okay. So then all I have to do is figure out an equation for Q. So Q then is really equal to that distance from the neutral axis to the centroid of the area above where we're trying to find that shear. So in this case, I'd have to find the centroid of this area here and then find the distance from there to there. Okay? And then it's equal to the area. So we could put the area there, this being the area. Well, why don't I go ahead and call this distance? I need something to call that. I'll call that y. So I can say that Q is going to be equal to, let's see, what's the distance to the centroid? I'm going to have y plus what? That gets me up to there. And then I need to have 2.75 minus y over 2. Is that right? Okay. So that's the distance. I have to go up this distance y. That gets me up to this point. And then I have to take half of that distance there. So I take 2.75, I subtract y, and I divide it by 2. And that gives me that little distance right there. Okay. Now the area, I will get that similarly. I'm going to have to take 3.5, and then I will multiply that by what? This distance there, right? Which is 2.75 minus y. Okay. So I think we should be good with that. So we come up with kind of an awkward second order equation, but if you run through the math on this, you'll find that Q turns out to be 13.23 minus 1.75 y squared. Okay. So we get this second order term out of that thing. So if I put this into the expression for tau, I could say that the shear stress tau is equal to VQ divided by IB. So I have 2,000 pounds times this Q, which is 13.23 minus 1.75 y squared. This would be in inches cubed. and then I would divide by I, which was 48.5, and that's inches to the fourth, and multiply then by 3.5. That's the B dimension, and that's inches. So when you get done with the units, you come up with PSI. If you do a units analysis on this, recognizing that would be inches cubed, should be in good shape. When you run through, you're just going to find this constant and multiply that times that polynomial, and you'll get 155.8 minus 20.6 y squared, and that would be PSI if you're keeping track of the unit. So 155.8 minus 20.6 y squared. So if we look at plotting this thing, we look at the side view of this beam. So we've cut through this thing, and it's got some neutral axes here. We'd recognize that this would be a second order function, and it would come to the maximum point right here. What's that maximum going to be? Well, the maximum is at y is equal to 0, and let's see, what's that turn out to be? 155.8 psi. And where's the minimum? The minimum is when y is going to be equal to either plus or minus 2.75, right? You pop either plus or minus 2.75 into this equation up here, and what does it turn out to be? 0 psi. You don't have any shear on that outside edge, so it goes from 0 up here to the maximum value there. Questions with that? So while we said that with our bending stresses we had 0 at the middle, we actually have maximum shear stresses at the middle. So before we start cutting the middle out of everything, because there's no bending stresses in there, we have to be careful there are shear stresses. Although shear stresses are, in many cases, are not as difficult to deal with as bending stresses. Questions with that then?
That's just for a section of square. Or
rectangular. Mm-hmm.
On the practice exam, we get something where it's T-shaped.
Okay. So we could segue into this problem. Thank you. They're going to think that I plant these questions, right? Okay. So this is not the T section. This is a I section. But what I'd like to do in this one is plot the shear stress over that section. You bring up a good point. It's going to be quite a bit different than it is for the rectangular section. So with this one, let's see if we can do that. To do this, if I look at a side view of this this I-beam, it's going to look something like this. There's the top flange, and then you have the web, and then you have the bottom flange. And if you're you're struggling to remember that, this would be the neutral axes then. This is a side view of what do I have up there. Remember that your fingers, what do they call your fingers sometimes? Phalanges. And what's the little piece of skin between your fingers? Your web. A web of skin there. So you have the flanges, and then between the flanges is the web. So that's a fairly easy way to remember that. And when we look at a beam like this, the flanges, the top and the bottom flanges, that's all about carrying the bending predominantly. Whereas the web, that's all about carrying the shear. Okay? So that's kind of what's going on in that I shape there. Well, let's look at this. I think what I'm going to need to do is I'm going to really need to find out what, and I think I can just do this for half of this. I'll do this for the top half, and presumably what's happening, because it's symmetrical, what's happening on the top half would be the same thing that's going on the bottom half. So with this geometry here, I'm going to look for the shear stress here, tau at y is equal to, what, 4 plus 2 is 6. And then I'm going to look at it right here, where the shear stress at y is equal to, I'm going to call this 4 plus. So just a little above 4, right? At 4 it's confusing. At 4 I'm right here, and I don't know really what the width is. But I'm going to say just a little over 4, then I get up into there and I know what the width is. Now likewise, I'm going to come down here and I'm going to talk about the shear stress tau at y is equal to what? 4 minus, just a little less than 4. Okay? And then, of course, I'm going to have to do the shear stress tau at the neutral axes, which is probably the most difficult. So let's do this. If you're doing group study, you're going to volunteer for the y is equal to 6. So tau at y is equal to 6 inches. What's that going to look like? It's equal to 0, isn't it? Because I remember we're using the equation here that the shear stress tau is equal to VQ divided by IB. What's Q? The area above this point. Is there any area above there? No. So Q is equal to 0. It's because Q was equal to 0. Okay, so then we look at this one. We'll look now at the shear stress at y is equal to 4 plus. So we're just a little bit above this interface. We're up into the flanges. So we're going to have to actually do some work on this. The shear stress tau would then be equal to, we're told that shear is 1,000, I is 693. If you want practice for I, you can go back through that. The only reason I'm not spending time doing that is that we get to a point where we can only do one problem per lecture. But if you want some practice, that'd be a good thing to practice. So we've got then V, that's that 1,000 pounds. And then what's Q going to be on this thing? Well, what's the area above there? 2 times 6, that's 12. Times what's the distance? 4 plus 1, 5. Is that right? Ah. Because, I mean, you might say, well, doesn't the area change because we're slightly above there? Well, we're talking about plus like 0.00000, something. We're just barely up into that flange, so it hasn't affected the area, hasn't affected the distance to the centroid. Now I have to divide by I, 693, and what is B? Well, if I'm up in here, B has to be what? 6. So when I run through the numbers there, I end up with 14.4 psi. Okay, so I have 0. At 14.4 psi. Let me continue on and talk about the shear stress at y equals 4 minus, a little less than 4 inches. It would be exactly the same thing with one important difference. Tau is going to be equal to 1,000, and you can run through the units on this. They will work out with the units that we're using. This would still be 12 times 5 times 693. What's the important difference? Yeah, my width, my B dimension is now not 6, but rather what? I guess I didn't tell you that, did I? Okay, this is given. 2 inches. So what's B? 2 inches. So as you can imagine, this number is quite a bit higher. 43.3 psi. So we got something that's looking like this. It's starting out at 0 here. And then it's a second order curve, right? We saw this clearly as a second order curve. So we're going to go second order to a point that's right there, and that has a value of what? 14.4. Then we have a discontinuity. It jumps up to 43.3. And now what? Now I need to come down and find the shear at the neutral axes. And that should be the largest. Tau at the neutral axes, which should be tau maximum for this problem. So let's see if we can do that. So we're going to have a 1,000 times, and then Q is going to be kind of difficult on this one. I'll give myself some room. We still have the 693, and our B dimension is still 2 inches. So now I need to do Q. And what I'm going to have to do with Q is I'm going to break this up. I'm going to have to find Q for this piece here, and then I'm going to have to find Q for that piece there. So let me go through that. That would be 6 times 2. That's the area of that upper piece, times 5, right? Okay, so that's for that piece there. And then I'm going to have to add to that, what's the area there? 4 times 2. So that's for that piece. And let's see, the distance to its centroid is going to be what? 4? No, let's see, this is, what's this total? That's 4 there, so half of that would be 2, wouldn't it? Okay. So you see where that Q comes from? I just have to put those two pieces together. I had that top flange, and then this is the piece of the web. So when you run through the numbers on this, you come up with hopefully something greater than 43.3, and it is indeed 54.8 psi. So this drops down here second order to 54.8 psi. And we can, of course, then just mirror this down below if you want to. Starting out here, we go to there, like that, and that. So your largest shear stress is 54.8 psi. You have a pretty good discontinuity across the web flange interface. Questions with that? So really the trick in here is figuring out what B is and then certainly calculating Q. So do some of those homework problems. That'll give you good practice on that.
For the B in this bottom equation,
okay.
The 4 minus the 2 inches, B in the 4 minus.
All right. Okay.
Where does the 2 inches?
There's 2 inches? Well, remember, if I'm not quite 4 inches, if I'm just a little under 4 inches, I'm like right in there, right?
Right.
So that would be that thickness between there. Okay.
And then when you wouldn't account for the thickness up above at all? Right?
Not if we're concerned about the shear stress up here. Other questions? Yes?
What causes that discontinuity right there? The 43.3 on our graph. Is that because of the geometry?
It's really strictly this number here because of the geometry, because of the width of the web or the flange. Other questions? Well, let's try something that comes up all the time, and it's predicting the maximum shear stress in rectangular beams. So rather than having to grind through this expression, tau is equal to VQ divided by IB all the time, for rectangular beams, if I look at a rectangular beam, where is the maximum going to occur? Should occur at the neutral axis, right? If this is the neutral axis, this is also the location of tau max. So let's talk about this. If I say that this has some base dimension and it has some height, the total height of this thing or the depth of it, the shear stress is going to be equal to V and then Q. If I want to try and find Q at this point, what's that going to be? Well, the area above there is what? H over 2 times the base dimension B, and then I have to multiply that by the distance to the centroid of that area, which is what? H over 4. Now I'm going to divide by I, which is base times height cubed over 12, and then B is really what? Well, B is B, isn't it? Okay. So I can try and tidy this up. What is this going to turn out to be? V divided by, let's see, I'll have H squared with a B there. We get 2 times 4 ends up with an 8 there, and I end up then with a 12 in the numerator, and I will have B squared and H cubed, right? So I get to cancel that with that, and I get to cancel that with that, and I can say that this turns out to be equal to 12 over 8 times V divided by B times H. Do we have another way of expressing B times H? Yeah, it's the area. So I could just say that this was 3 halves. That's a nicer way of saying 12 eighths. 3 halves V divided by A. So that's a quick way of getting tau max. which is probably oftentimes what we're interested in for a rectangular beam. Now this doesn't work for an I shape, it doesn't work for a T shape, it only works for a rectangular shape. But we use a lot of those rectangular shapes, so recognizing the simple equation 3/2 V over A can be a real time saver. You can start to do that in your head, whereas this equation is quite a bit more difficult to play with in your head. Well, with that, let's try a little more practical problem. So let's say someone's given us a beam design. We got a 8-foot opening, and we're going to design a beam for it, or maybe we'd call it a header. Sometimes we call it a header. 100 pounds per foot. We'd like to size the beam based on bending and shear. We'll use wood with about 1,000 psi bending and 100 psi for shear. That's about dug for number 2. I think it's about 95 psi, but we'll take 100 psi for shear max as we go through this example. So this is a little bit like the problem we did with the garage door beam or the garage door header. We usually start out with bending, figure out what the size is for bending, and then we check with shear. So if we look at this based on this right here, what's M, the moment max? Well, for distributed load, we know that that has to be what? WL squared divided by 8? I mean, you could go through the shear and moment diagram, but at the end you come up with WL squared over 8. We've done that many, many times. WL squared over 8. So we would have the weight, that's 100, times the length, which is 8 squared divided by 8, which I get, what, 800 pound-feet. Okay, and then I'm going to multiply this by 12, so I come up with 9,600 pound-inches. Okay. And they told us we could use 1,000 psi, so we take the section modulus S is going to be M divided by sigma. So I take 9,600 pound-inches and divide by sigma, 1,000 psi, which gives me then 9.6 inches cubed for my S value. And you could recognize that and say that, well, that's base times height squared over 6. And you could take a base dimension, probably 1.5 inches, and then figure out what the height is. It's probably a lot easier at this point just to grab this number and run into the table. So we got this table here. This is from the website, the same one we talked about last time. This is the one for saw lumber. So we want what? 9.6 for the section. So I'm going to presume that I'm doing strong axis bending, so I'm going to be looking at this one, the 1,1 axis. There's that base times height squared over 6, and I just head down here until I find at least 9.6, right? It's not going to take very much. Not near as much load or near as much span as we had in that garage door header. Looks like I get here 13.14 should do it fine. So what's our recommendation? 2 by 8. 2 by 8 should do it, shouldn't it? Okay. So let's try a 2 by 8. And we'll say we accounted for the dead load of the beam in there, so I don't have to go back through that. If you wanted to mess around with that, you get 2.6 pounds per foot. This is quite a bit larger than that 9, so I think we're probably okay. But we'll try a 2 by 8 on this thing. We know we're good for bending, but now we need to try this for shear. So what's our shear max going to be on this? Well, shear max is equal to the shear force, or I'm sorry, the equation that we just finished up with, that was 3/2 V over A, wasn't it? Well, let's see, I know what the area is because I have that 2 by 8, but what's the shear? Well, if I look at a shear diagram for this thing, what's that turn out to be? It jumps up by the reaction there, and then it goes down by that. So our maximum shear is really our reaction, isn't it? Whatever reaction that I have there and whatever reaction that I have there. Well, it's 8 feet long. We've got a total load of, what, 800 pounds, so this had better be 400? 400 pounds? So I can say that I have 3/2 times 400 divided by the area, which a 2 by 8 is going to be 1.5 times, what, 7 1/4? I didn't make up those rules, but let's see, 2 by 8, 1.5, 7 1/4, or you could look right here, you got your area right there, 10.88. So you got 10.88. So let's see, you're going to divide by about 10, so we're going to have 40 times that. About 60 psi, something like that, roughly. I guess if we grab our calculator and get a little better number. $55.1, anyone get that? Yeah. 55.1 psi. That is less than what? That's less than that 100. So are we good? Yeah, I think we're okay. So our answer would be a 2 by 8. That's our answer. Okay. So you can get through this fairly quick. Again, we did not deal with our bearing, the columns that this might be on, the footings that it might be on. We also haven't talked about deflection yet. We'll talk about deflection before the term is over, but we'd want to look at all of those things. But we did handle bending, and we did handle shear. That's more than we could have done a few days ago. Questions of that? I mean, if you didn't have the table, you would have probably assumed that, well, I'm going to try a 2 by, so you'd assume this at 1.5, and then you'd solve for h. You'd come up with what h is, and presumably you'd get something a little less than 7 1/4. That would tell you that you needed a 2 by 8. You could then run from there. For those of you going to structural design, if you have a column supporting this, you'll get to actually come in here on this shear diagram, the distance of your column, and take that as your maximum shear, which can actually help you a little bit. But we're not going to muddy the waters with that for now. We'll get into that when you do structural design, wood design. Questions with that process? So that was page 4. I'll record this as page 5. Well, the last thing I'd like to talk about today is finishing up talking about shear flow. This is the last subject we have to do with shear in beams, and actually then the homework section F, and also the material that would be on the exam. So I'm just going to finish this today, if you'll bear with me, and get to a nice stopping point. This would then be all the material that's on the exam when we get done with this. So if we look at shear flow, I'm going to say that shear flow, I'll define it with F. Some people use different symbols and whatnot. And I'm going to say that that's the shear stress times the base dimension of the beam, B, which would give me, if I make the substitution, VQ divided by IB. That's the equation we've used for the shear stress. And now I need to multiply it by that B, don't I? So I cancel the B in the numerator and denominator, and I get the shear force V times that Q term divided by I. So we get then that the shear flow is equal to VQ divided by I. And what that is actually shear force per length. Shear force per length. So it's going to be something like pounds per inch or newtons per meter or something like that. It's a shear force per length. And the reason we want this is if we're going to start to build up a beam, let's say that we take a top piece and a bottom piece like this. We're going to build this beam up, simply supported beam here. You could use it for cantilever beams too. And you want to put screws in this or nail it or weld it or glue it, depending on whatever you're using. The question comes up, how many nails should you put into this? What's the spacing? Okay. What's that spacing? And the fastener spacing is then pretty easy with shear flow. Fastener spacing is equal to the force per fastener. Okay, so if we have a nail that supports 100 pounds per nail, that's where that number goes. I guess we did a C in there, don't we? There we go. Force per fastener. And then I divide this by the shear flow, which is the shear force per length. So when I get done with this, I end up with length per fastener. Okay, so I know how often to place the fasteners. Yeah, it could be a screw, or it could be a nail, or it could be so much glue, or it could be so much weld. Okay, depending on what we're going to do. So let's just try an example on this. Let's say we're going to build up a composite beam like this. And we're going to take a 2x6, it looks like, and we're going to nail it to a 2x12, like that. And we're going to use, I think this is a number for 16D box nails. Okay. So when you could spend a lot of time talking about nail terminology and whatnot. If you go with hand-driven nails, usually there's two big categories for that. There is box and there's common. Box is usually more slender. Common are larger in diameter. Common are, of course, a lot easier to drive. They don't bend as easy. But remember, you buy nails by the pound, so you can get more nails if you buy box nails. So probably people tend to use more box nails. The numbers for box nails are slightly lower than common nails, but it's usually still more cost-effective to buy box nails. If you get into mechanically driven fasteners, pneumatically driven fasteners, then they usually go by different dimensions. This is, call this a 16 penny nail because that's kind of an antiquated term for English pennies for 100 nails. I think that's how that goes. A 16 penny nail is going to, I think, be about 3 1/4 inches in length. Okay, and the nail sizing goes up to 60D, which is about a 6-inch spike, and beyond that, usually they start just giving them with dimensions. So you might say, well, gee, I've driven a nail in the wall, a 16 penny nail, and I bet it would hold more than that. I mean, I'm around 200 pounds, and I could maybe grab that and hang from it. Well, remember, this probably has quite a bit of safety factor in it. What if it goes into a bad spot in the wood, it misses something, it cracks the wood slightly? So usually we've got some pretty heavy safety factors in that number. So, well, let's see if we can do this then. So as I go through this problem, what I'm going to need to do is I'm going to need to calculate the Q value in here. So I want to do Q at this interface, because that's what the nail is supporting, the interface between the top of this 2x12 and the bottom of this 2x6. So I'm going to try and find Q in there. And what's that turn out to be? Well, the area above it's the area of the 2x6, so 1.5 times 5.5. And then the distance to the centroid. Well, if you go through the centroid on this, and I'm not going to reproduce all of this again, but if you look at this, the neutral axis, the centroid on this, is 7.72 inches up from the bottom. Okay, 7.72 inches, which would mean that we would be left with a dimension here that is 3.53 up to the underside of that. Okay. And if you go, once you know that, then you can calculate I is 404.7 inches to the fourth. So again, if you want some extra practice on finding centroids and calculating I, that would be a good example for you. I'm not going to belabor the problem by going through that. We'll just say that we know that. So with that, when I'm calculating Q, what am I going to need to do in terms of the distance from the centroid here, the neutral axis, to the centroid of that piece up there? What's that going to be? Probably 3.53 plus what? 1.5 divided by 2. Will that do it? 3.53 gets me up to there, and then 1.5 divided by 2 moves me to the centroid of that piece. So when you get through that, Q turns out to be equal to 35.31 inches cubed. Well, we don't need that many significant figures. But as I calculate then the shear flow F, which is VQ divided by I can say that this is, our maximum shear will be at a reaction here. And if we were to do a shear diagram on this, it jumps up, comes down like that. So our maximum shear is what our reaction is, right? So we've got then 300 pounds times 300 pounds times Q, which is 35.3 inches cubed, divided by I, which is 404.7 inches to the fourth. So when you run through this, you get 26.17 pounds per inch. And so I can come up with my spacing then. My spacing is 108 pounds per nail. We've got a 16-penny nail up there. 108 pounds per nail divided by 26.17 pounds per inch, which gives me 4.12 inches per nail. So what should my spacing be? Could I say 4.5? That'd be spaced too far apart, right? I probably don't want to send on-center spacing of 4.12 out to the shop, right? No one wants to deal with that. There's not a repeating mark on a tape measure that makes sense at 4.12. Because then I put one at 4.12 and the next one's at what? 8.24. It just is a mess. So what's our on-center spacing? I mean, this is the number we come up with in our calculation, and then so many times we have to make the good judgment call. What do we put the on-center spacing? Yeah, 4. I mean, people can say, well, how about 4 and an 8 or something like that? I mean, 4 makes a lot more sense, doesn't it? 4 inches on center. Okay. Now, the other thing, looking at this shear diagram, is we're talking about the shear right there where it's the maximum. What if we look at the S right there? The shear is a lot less there, isn't it? So our required spacing would actually be less. And I mean, if we really wanted to make a big deal about this, if I were to look down, if I were to have some top view on this thing, looking down, my nail spacing might be like this. I'd have the nails very close together here, and then I could start to stretch them out, and then I'd have to have them very close together there, right? Now, you as an engineer has to figure out, is it worth my design time to do that? I mean, if they're just making one of these, we're probably better off just to send it out 4 inches on center and be done with it, right? If this is something they're going to do over and over again, then maybe we could spend the time to go through this analysis and come up with this spacing. The only problem, too, is we have to figure out a way of conveying this, because if this is what we want, you can imagine, if you don't convey this very carefully, what are you going to get? Doesn't take much imagination to figure out someone might come up with that, right? And that's not what we want at all. So you got to figure out ways to make things foolproof. I mean, if this is something that we're maybe we're using a robotic nailing system or something, and we're going to be the ones programming it, this is probably just fine. If we're trying to rely on people to do it, maybe we're going to have to make a template. We make a template, and we drill the holes in this template where they should be, and just have them lay that on there, run a strip of spray paint down it, and then they got to mark where the nails go or something like that, right? Okay. But probably if they're not making too many of these, 4 inches on center and have it look like this is probably the most foolproof way, right? I mean, it took me a little while when I did consulting. You'd send plans out to the job site and it didn't work out. And I learned that a lot of people on the job site are illiterate. And I'm not trying to be mean about this. Okay? They couldn't read the plans. You send a note out, they just couldn't read it. Okay? So you had to figure out ways with pictures and whatnot to convey that message and to make sure that what you wanted got built. Okay? I mean, you might say, well, that's their problem. Well, at the end, it's kind of your problem. So some things to think about. A lot of times, people will say, oh, this is our answer here. No, we're a few steps away from something we want to send out to the shop with that. So, I mean, this is basically math here, right? The engineering goes from this number to make something that we can actually get someone to build. I mean, it's our obligation to make this foolproof, right? We always have an expression, maybe it's not a very nice expression, but we got to make it foolproof. We don't have to make it damn foolproof, but we have to make it foolproof. Okay? So, anyway, this you can get into this with, name your favorite fasteners, screws, nails, or whatnot. This comes up quite a bit when you're welding. Let's say that we're going to, where are my page numbers? We're at 7. We're here at 8. So you take this piece of steel and you bring another piece of steel into it. Maybe you're even going to make an I-beam out of it. Maybe you're going to make a bridge and you need some great big I-beam. And you want to put this weld in here. Okay? You want to put the smallest weld possible. Because as you have to put a larger weld in there, you got to buy more weld material. You have to pay the labor to put that in there. And the biggest thing probably you want to try and avoid is the heat distortion. Okay, heat can be a real killer on this thing as you try and weld this up. So the smallest amount of weld that you put in there, that's going to pay off for you. You might wonder, well, where does this ever come up? I mean, isn't it more cost effective just to put a rectangular beam in this thing and be done with it? And a lot of times it is. I got into a pretty good example of this. We had a wooden roof structure, so you had your sheathing and your wood on top of it, and then the roof joists sat in here like this. They're usually shown with a cross across them like that. And this is, I mean, if you have a wall here and a wall here, and you put the joist across it like this, and then you put your sheathing on it, I'm taking a section view and looking at it like this. Okay? So it's a nice vaulted ceiling like this. And I said that they needed to have, I believe it was 2x12s, 16 inches on center. I would have said Doug Fir number 2, 16 inches on center. And then I always put a maximum span here. Max, span. Okay. So everyone knows what the score is. Well, I think, they must have known more than I did, because they came along and what they put in, they put a 2x10. Okay? That's a pretty long span. And the plan said 2x12. They put a 2x10 in. They nailed this on. They nailed the roof on. It was in the wintertime. They even had the electrician drill some holes and put wires through it. Okay, so tearing this out was not a real easy option. Okay, so they called me up. Well, what can we do? Okay, well, let me run some numbers. So what I said is, what if we put a 2x4 like this and nail that in? And nail that in, and then we look at the roof sheathing, and we look at support from that. And the concrete guys will get into this quite a bit. You take a beam, maybe an I-beam, like this one, and what you're going to do is they're going to weld a stud onto this great big glorified nail. It's about 1/2 inch or 3/4 inch in diameter. And then when they come in here and they pour concrete on this, that's how this floor that you're sitting on is made. They've got the I-beams, then they put this pan deck here. And then they pour concrete over this, and this stud transfers the shear into the concrete. So you get to have this thing acting like a composite beam. So I decided, well, I'd try that with the wood here. Okay? And it's a little dubious because your sheathing has breaks, and I couldn't make it work out. So I said, well, what if I put another 2x4 up here? And I actually got it to work out. Okay. They didn't like that. They didn't want to have to nail the 2x4s on the side. I said, well, the other option is you tear it down and put the 2x12s in, right? Then it looked really good when you're done. Oh, well, this looks better. Okay, this option sounded better all the time, isn't it? Okay. Part of dealing with people is how to talk to them, right? Okay. But that worked pretty well for that solution. The other thing sometimes you run into, you get these houses where you have a garage like this, and then they build the house up over the top like that. You got the garage door here, right? And usually you end up with a large beam in here, okay? And usually it's a great big glue lam beam. And with glue lams, if you look at a beam going back to bending, with loading like this, you end up with compression here and tension there, right? And let's see, knots and kind of bad, almost rotten wood. Works pretty well for compression, right? But how about tension? You want good wood in tension. You don't want to have a bunch of big knots and whatnot. So what they do, if you have a, we call it an unbalanced beam, they put the really good wood in the bottom and they put kind of junk in the top. That actually works really well, okay? And you get the beam for less money. The only problem is the beam clearly is marked on the top. It says TOP in great big letters, okay? Huge letters, 3 inches tall, because you don't want to put it upside down. So it's always a bad day when you walk into a structure and you look up and you see TOP. Okay? And final framing inspection is after they put the plumbing in this thing, after they put the electrical in this thing, they've got the roof on it, okay? They got the sheetrocker standing there jumping on one leg and the other, the insulator jumping on one leg and the other. They want to get this thing done. I worked with someone that from the time they got the building permits till the time they handed the customer the key, this was in the building boom before things fell apart, was less than 30 days. They built a house in less than 30 days. Okay, so it moved right along. So you have a problem here. Okay, you don't want to tear that beam out. You got to tear half the house out to get that beam out. So what do? Well, you come in here and you put a piece of steel on this thing and you lag it to the bottom of that, so you effectively build this composite beam. Okay? And figuring out what your lag spacing is exactly what you did in the previous problem. Now the civil engineers are going to go on to do a lot of this, and not because they're fixing people's mistakes, but from the get-go. What if we look at a concrete beam? If we say that this example was a concrete beam, again with compression, does concrete handle compression well? Yeah, but how about tension? Not so good. So what do? We put reinforcing bar in there, don't we? And you will actually analyze that very similarly to what I had to do to retrofit that steel beam. I mean that wood beam. And sometimes this comes along pretty innocently, not because people make mistakes, but maybe they want to add to it. They have this beam and they want to put more load. They want to maybe put another story up here. Well, they actually have some really interesting carbon fibers that you can apply to the bottom of beams and whatnot. It all uses some of this same technology and technique. So that's kind of interesting. Those of you going into civil, I take a close look at structural. It's a fun area. There's no lack of humor either. Okay, so you always see things it just shakes your head. You just shake your head. But anyway, any questions with that? I think that gets us to a good stopping point.